Josh, and today I want to talk about performance in Unity and testing out a few of the assumptions and maybe preconceptions that we have. So let's get straight to it. So here we've got Unity and we've got the performance profiler, which you can get from going from analysis profiler. And what I've got is on this game object, I've got this little script called MemoryAlec, and in here I've got a number of tests. And just to quickly explain what's going on, so it's a little bit of initial setup where I create a number of arrays of stuff. So I've got sort of 4,000 array elements, an int, and then a string that for some reason is 4024 bytes or 4024 characters in length. And then I start this test controller, and all the test controller does, basically, the important bit of it is it yields this test duration, which is set to 10 seconds, and then it stops. So that's all that does. And then you can uncomment one of these and run one of the tests. So I'll just show you what I mean. So let's just uncomment this one. So this is Alec test new string. We have a look at that. Now, all these tests are going to do roughly the same sort of thing, same kind of pattern. They do a while loop. They'll carry on running until the test controller kills them off. And then they wait for the end of the frame, and then they do something. And in this case, what we're going to do is we're going to allocate a 424 character string to hello. And we're going to do that on every frame. And we're going to see whether we create any allocations. So let's just have a look at this, see how it runs. So let's just make sure I've saved that. Go back to Unity, and then we run. So you see the profile will do its thing. The code's running for 10 seconds and it'll just finish. Yep, there we go, test finished. So we can come back in here and we can use the scrubber and come along here. And when we're looking at GC-Alec here, so we've got 7.9 we can see, and these are going to be roughly per frame. So we can see we're getting a lot of 7.9s, and we can dig into one of these because we've got a deep profile on. And we can see that the 7.9 is inside the move next. So as we're enumerating over this, so let's have a look at that. What does that mean? So if we come down to our code, so it looks like as we're going over this, creating this thing here, it's got some kind of enumeration in here. That's causing the 7.9k of allocation, which we kind of expect that we're going to be allocating memory to do that. So we know that this test produces allocations. But why is that important? Well, the reason that it's important is you've got a fixed amount of memory, roughly speaking, when you're running an app in .NET. And what happens in the background is it will clean itself up of pieces of memory that are no longer needed. And it will do this depending on how stressed it is. So if you've got not much memory, then you're going to get more garbage cleaning. And when it does a garbage clean, it has to stop all the threads. So obviously, if you're in the middle of doing lots of frames per game, anything that stops and pauses while it's doing something is going to be bad news for your game. Now, obviously, if you're a desktop application and you've got tons of memory, then you're probably not going to see this very often. But if you've got a mobile app or you haven't got much memory, when you've got a big game that has lots of big objects, then if this happens, then this could be bad news. So this is why you want to pay attention to how many allocations you're having. And it's important as well with these multiple frame ones that you don't see this happening a lot like we're seeing here, because that will more likely cause what's called first generation garbage collection. These small objects are going to get garbage collected. It's not too bad to put the stuff right at the beginning of the app, do the caching of objects, because that they become kind of more long-lived objects as far as .NET concerned, and they won't get cleaned up in the garbage collection as often, anywhere near as often, only if the memory gets really stressed. So this is the pattern. This is what I'm using to do the tests, and I've got a lot of tests. So let's just come back to the code. You can see here that for all this code, all these different tests I've coded up, we can just take a look at maybe another one. Let's just take a look at the material allocation. So if you look at this one here, what I'm testing here is that we're inside the loop. So we're doing this per frame. We're trying to find a tag, and we're getting the component renderer from that tag, and then we're changing its color. So we can see whether this is actually going to create lots of horrible memory allocations. So we can run this. You can see there we've got a cube flashing away in the middle, changing color. Again, after 10 seconds, it's finished, so we can use a scrubber. We can come along here and we can see that actually this is pretty good. We're not seeing any additional allocations popping up. We can just make sure of that. Just drop this down. Yeah, it's some little flicker there, nothing. Yeah, so that's actually, as far as memory allocation goes, it's perfectly fine code. So we don't have to worry about that. There may be other issues like performance, but from pure memory allocation point of view, this code is fine. So we can prove some of these concepts that we keep hearing about. Another one perhaps that we hear a lot about is for each. So let's take a look at this. So a classic one is the boxing issue that used to be a case in certainly Mono, in early versions of Mono. So is it still the case? Now we've moved over to .NET Standard and 4.x. So here we've got an array of ints. So it's literally just an array of ints, and we're going to for each over them. So in theory, that should be boxing. We'll be told that this is going to do boxing. So let's have a look. So again, we're going to run for 10 seconds. It's doing its thing. And we get to the end of the 10 seconds, and we use our scrubber, and no additional allocations. So this looks pretty clean. So maybe for each isn't evil, as we have been told quite frequently. So that's not to say that there isn't some evil in here somewhere, as we're doing some nasty tests. So let's have a look at, say, I think this one. So in here we've got an array of ints, but this time we're going to force it into a list, and then we're going to start looking at it. In fact, that code, yeah, we're just enumerating over that list. Let's see if that is actually going to cause us any kind of allocation issues. So let's just run that. And the graph looks a little bit more interesting. So we can come into here. And yes, indeed, we are getting some allocations. So we can have a look at this. And we can see that our toList down here, the constructor of the list itself, is producing 15.7 kilobytes. And then, yeah, so that's kind of bad news. It's not, I mean, it's quite a big number, really, given that we're just looping over something. So obviously you don't want to be doing that toList too often. Okay. So let's have a look at the for loops. So the for loop over a string array, that sounds like it could be quite interesting. So we're coming in here. We've got an array of strings that in theory aren't a value type. So when we do this array of strings here, we're grabbing one. We're going to get some kind of unboxing allocation occurring here. Let's have a little look. don't worry, I'm not going to go through all of them. Let's just a quick test on this one. Okay, that's finished. So we can move our scrubber along here, and sure enough, we're not seeing any horrible looking allocations. So this is all good. Let's just show you one that is probably quite expensive. We'll go down and have a look at our link ones. So let's have a look at this one. I say quite expensive, I mean really. Got an array of ints. So again, we're not in the reference land, we're in the value land. And we're going to do a where clause over it, so we're going to get all of them. And then we're going to convert that to a list. So we've got two things going on here. And then we're going to get the value back from that. So we're going to get an array of ints out of that. Yeah, we should do for each. Yeah, I'm doing it for each over it as well. So in theory, this is kind of, the worst case scenario. Let's have a look. Is it really that bad? So it looks like we are using it, yeah. So let's just run. Again, another 10 seconds. And yeah, again, it's looking a little bit more interesting. So yeah, we can see some stuff going on here. So let's have a look at this one. We've got some allocations here. It looks like it's all the way down here. Doing the add. So this add mechanism is allocating our capacity. So that seems to be the thing that's hitting us with the 32K. So that's doing the to list. So yeah, that's quite painful. And then we get a little bit here on the where. So constructing the where clause. It's giving us a few bytes as well. So again, this is happening every frame. And if you did have something like this that's happening every frame, obviously this would add up quite quickly and we would probably start garbage collecting and hurting ourselves. So yeah, there's definitely some issues. You can't just go mad with a link, certainly, and just put it everywhere and expect it not to give you some allocations. So use it wisely. Always test. Okay, so let me just bring up the spreadsheet. Yay, exciting spreadsheets. So can I get this to get a little bit bigger? Yeah, there we go. Okay, so what I did is I ran these tests and I listed where something was going to go a bit nasty. So you can see most of these things are okay. The for each over an int list to array. So yeah, it's doing the to list is expensive or costs us. Doing a to array from a list, that costs us. So we do these conversions from one thing to another. We want to try and avoid doing that. This is doing an of it ints. So this is where you take a list and you convert it to ints. Again, you can see that's particularly painful. So you probably want to avoid doing that as much as you can. Collections, they are quite good in some ways. If you're not really sure what's going on or what kind of data types you've got, these have an overhead, but it's a very small overhead. So these can be quite useful. Again, looking at so that's the for each. If you're doing a for loop going over something, then they're fine for just arrays and lists and stuff. That's absolutely fine. But again, if you start doing two arrays, then that gets a bit painful. There's a to list in here. Let me just have a look at that one. So I'm going to amend it. That's rubbish. Looks like I had a copy and paste error there. Yeah, that's fine. So the to array, that's a bit more like it. So the to array, obviously we're getting hit with the conversion to two arrays. Allocate test for ints. Again, doing the of, that's costing us. And we're also doing a to list, which is costing us. Don't want to be doing that. For looping over the collection, that's much better. You don't even get the overhead like you do with for each, because the for each is using the enumerator. This collections doesn't need the enumerator, so that's good news. So yeah, so this is the list here. really the kind of takeaway is avoid doing 2 lists and 2 arrays. They seem to be the thing that's going to really cost you. Otherwise, most of the other things are fine until you get to sort of link, and then you just got to be a bit more interesting. Materials tests, that's quite interesting because let's just look at one of those. They're interesting because they worked exactly how I thought they worked, and that never happens out the bat for me. So this is the kind of code I would write normally for the materials. So we do a find object once, we get our render and cache it, and then we're just changing the color. Now we don't need to go and cache the material because the material is just a child of the renderer. It's already on there. It's just a property of the renderer. It's already referenced. It's not going to cause us any problems. It's a bit of a performance problem to have to go via the renderer in terms of pure speed. So you're better off caching the material in this case. But the real shock was these tests, or was shock to me, was that if I put that find object inside of the loop, so we're not caching this anymore, this again produced no additional Alex. And even when I forced it to start stacking stuff rather than putting stuff in the heap, so I've got an action here that's doing the color change, but the isBlue is coming in out of scope. So this should, in theory, stack these in memory. And then when this runs, again, I'm not seeing any heap allocation. So whilst that's expected, I was just going to see whether I could catch it out by putting stuff on a stack. But no, that one ran fine as well. So yeah, the only other thing to talk about, I guess, a little bit is the two different versions of .NET that we're running. So we've got standard and the 4.x runs. They didn't produce any different results. And also the engine itself, so we had Mono and the IL2 engines, and they didn't produce any different results either. So yeah, I mean, I confess to these, I didn't rerun all the tests. I ran samples, but from the samples, they were all identical. So hopefully that'll give you not necessarily any clues about which exact mechanism you should be using and when. It's really more to say that when you are using these kind of looping constructs, you need to think about what you want to use and try and find the best technique straight from the bat. But really, you need to run the performance test afterwards and make sure that you're not getting some really heavy allocations like these ones, especially like that one there, because they will cost you, and they cost you dearly. So it's always worth doing a performance test after you've finished your coding. Well, I hope that hasn't been too confusing, and I hope it's been of some use. Thanks.